This video is about the differences between the terms voltage and potential. Sometimes in practice there's great confusion between these two. They are very similar, they also have the same unit, and this video is about clearly separating the two and also conducting a small experiment using a multimeter and a simple circuit to show you what voltage is and what potential means. My name is Andreas from The Fearless Engineer, and here we go. Now this video is about the differences between the two expressions of voltage and potential. In practice there's lots of confusion between these two because they are so similar, and by the end of this video you will know what the difference is, what the commonalities are, and in which situation you might better be advised to use potential and when voltage is the correct expression you should use to describe, for example, the behavior of a certain element in a circuit. You will learn here that both of these two have the same unit, it's the volt, but potential is a measure of the potential energy of a single point, of one point, relative to the negative terminal of, let's say, a battery, and voltage, on the other hand, describes the energy difference between the 2 points. Voltage always relates to 2 points and is about differences, and potential is about a single point and its difference towards the negative terminal of the battery. That's, in a nutshell, what both expressions are about. But we will also conduct an experiment in this video here, and in this experiment we will look at voltages in a circuit and also potentials in a circuit, and we will use a multimeter to do so and measure the voltage drop, for example, across an LED, light emitting diode, also across resistors. So before we start with the experiment, let's look at a bit of theory first. And if you have seen the video on voltage, you might know that charges in the electric field, that they have a potential energy which depends on the position of these charges within the field. You can see this in the small diagram here on the left side. Here you can see a battery with a positive pole on the bottom and a negative pole or terminal on the top, which are separated by a distance L from each other. And between these two poles, ranging from the positive to the negative pole, we have an electric field. And in this electric field, there are 3 charges in this example. The charges 1 and 2, they are on the same equipotential line of the field, which means they have the same distance towards the positive or negative pole, and they have the same potential energy, which is related to this equipotential line. You can very well compare this to a map, a topographical map, where you walk around, let's say, the circumference of a hill, and if you walk along a height line, you will never change your height above ground if you strictly follow this topological height line, and it's the same for the equipotential lines in the electric field. So both charges, they have the same potential energy if the charges are of equal size, of equal magnitude. And this third charge, it has a different potential energy because its distance from the positive or negative pole differs from the charges 1 and 2. And now we get to one of the core ideas in this video, which is the electric potential. We have already talked about potential energy, and now we are talking about this expression here, the electric potential phi. And the idea which we have followed up until now is that we can express the potential energy of a certain charge at a position in space, 1 and 2 and also 3, and it depends on 3 factors. The amount of charge, the distance to one of the terminals, and also the strength of the electric field. And what we want to do now is we want to answer the question for a given charge, let's say charge number 4, what the potential energy of this charge number 4, let's say at position phi A, is going to be. So what we want to do is we want to describe the properties of this equipotential line, but we want to make this independent of charge. So we can just take a new amount of charge and say, okay, if we know phi A, the properties of this equipotential line, then we can take any amount of charge which we want and move it to this position and then say, okay, this amount of charge at this position has this and that potential energy. So the electric potential expresses the possibility for a certain charge to attain a potential energy at a certain point in space. And the electric potential is described by the product of length and electric field. So phi A is the position here of the first equipotential line and the strength of the electric field which permeates this space here. And if we multiply it with the amount of charge for charge number 2, we get the potential energy of charge number 2 at this electric potential here. That's the first expression which we want to look at. And the second, the definition of voltage, which you can see here, simply relates two equipotential lines to each other. So if we say we want to understand the change in potential energy if we move charge number 2 to this new position phi b, then we can use this concept of voltage to do exactly this. We can say, okay, let's take the electric potential at position number B, subtract from it the electric potential at position number A, and then we get the voltage UAB. And if we move charge number 2 from position phi A to position phi B, then it will lose some of its potential energy, and this loss of potential energy is described by the amount of charge multiplied with the voltage UAB, which drops from A to B. Basically, when we get back to the example with the apple, the voltage can best be described as the loss of potential energy if the apple drops from one position to another position. Let's say it drops from 2 meters to 1 meter, then we can describe the loss of energy in this falling motion from position 1 to position 2 as the voltage drop of the apple, so to speak. Now let's explore the experimental setup with which we want to explore the differences in an experiment between voltage and potential. You can see a battery here, 9 volt block battery with its positive terminal on the left, the negative on the right. Let's follow the path of the electrons here. They leave the negative terminal, follow this, this conductor here, reach the first element of the circuit, which is an LED. Then they pass the LED, which will emit a certain amount of light. Once they have crossed or passed the LED, then the electrons pass a first resistor, pass a second resistor. These two will experience the same electrons moving through them, which means they are connected in series. And once the second resistor is left behind, the electrons will reach the positive terminal of the battery. That's the closed, unbranched circuit which we will use in the experiment here. Now let's look at the first experiment, which is about potential. And as we have seen before, potential always relates a certain position in space, a certain equipotential line, relative to the negative terminal of the voltage source, in this case the battery. So we connect the ground connector of the multimeter always to the negative terminal of the battery. We leave it there, and then we move around the red terminal here, or the voltage terminal of the multimeter, first to position number 1, which connects directly to the positive terminal of the battery. Then we move to position number 2 between the two resistors, then to position number 3 just before the LED, and then to position number 4. And we will look at the measurements to see what the electric potential at these various positions in relation to the negative terminal of the battery actually is. In the next experiment, what we are doing now is we want to measure the voltage drop across the various components. So in order to do so, we also have to move around the black cable here, and voltage drop always means the difference in electric potential between 2 points. And we still have these points here, 1, 2, 3, 4, just as in the previous experiment, but now we are measuring the voltage drop in this example here across the second resistor. And in order to do so, we connect the red probe to position number 2 and the black probe to position number 3. And using the multimeter, we then will be able to measure the voltage drop across this resistor here. We're also going to do this for the LED and for the first resistor, and also, of course, for the battery. Okay, so before we start with the actual measurement, let's quickly look at the setup of the circuit board here. What you can see here is a so-called breadboard, and this breadboard is designed as follows. These outer connectors are the so-called power rails, and they are connected from top to bottom. So this means that the plus cable leading to the battery, or leading to the battery in a few seconds, is connected all the way down to the bottom with all the holes in the same column here. And it's also connected with this jumper cable here, with this connector which leads into the center part, about which I will talk in a few seconds. On the other side, we have the negative terminal of the battery, which is connected to another power rail, which is connected in the same manner from top to bottom. And this negative connector here leads into this jumper cable, which leads to one of the legs of one of the connectors of the red LED, which you can see here on the board. Now, in the center part, the connection between the different holes of the breadboard is rotated by 90 degrees, which means all the holes in one row are connected to each other. So if I, for example, take row number 5, all the 5 holes in row number 5 are electrically connected to each other. However, the holes in the neighboring rows, 4 or 6, have no connection to row number 5. So power rails is top to bottom. The center part is always, the rows are connected left to right. And now let's take a look at the circuit as it's designed here on this breadboard. If we follow the path of the current, the technical current direction, the current enters the breadboard here in the power rail, flows down to this jumper cable here, is directed into row number 7. From there, it takes its path through this resistor here, and from the resistor, once the electrons leave the resistor, they flow into the other jumper cable in the middle here, down to the second resistor, which has the same color code as the first one. So basically, the two are the same, plus minus a few percent for tolerance. And after the second resistor has been passed by the current, it flows down this jumper cable here and into the light emitting diode, the LED, which is going to light up as soon as I connect the battery to the battery clip. And after the electrons have passed through the LED, they flow back to the negative terminal of the LED. And the idea here is to show you the difference between potential and voltage. And in order to do so, the first thing we have to do is we have to connect the battery to the power clip, obviously, which I am doing right now. And as you can see, as soon as I connect the battery to the clip, you can see the LED light up a little bit. It's a faint glow. Maybe let's turn this a little bit more to the camera so you can see it better. Now you can see a faint red glow being emitted by the LED. Okay, let's first start with potential. The idea of potential is to measure the potential energy of the charges flowing through the circuit. And the thing you need to remember about potential is that it's always relative to ground zero, so to speak. So the negative terminal of the battery, this is going to be our reference point for the potential, which is why I am now connecting the negative measuring tip to the negative terminal. Now, if I start from the positive connector, you can see in the display of the voltmeter that the voltage which is provided by the battery is at 8.8 volts, which is roughly according to the specification, which says 9 volts, but it's a used battery, so maybe there's already some charges drained from the battery. So this is the full potential energy, the full potential which I am measuring now when I hold these tips directly against the terminals of the battery. When I move down, let's say to the beginning of the first resistor, you can see that the potential has decreased a little bit to 8.77 volts, so minus 0.02 volts, which is not much, but in the path from positive terminal to this resistor here, nothing much has happened, and the resistance of the parts in between is very, very low. But as soon as I move the measurement tip against this resistor here, you can see that the potential now has dropped significantly, down from almost 9 volts to 5.5 volts roughly. So the electrons have lost potential energy. When I move to the other side of the second resistor, you can see that the drop is even more significant now, from 8 volts down to from 9 volts down to 2.2 volts roughly. So again, once they have passed through the second resistor, they have lost potential energy, which is represented by the potential in volts, which you can see on the display of the voltmeter here. As soon as they have crossed the LED, which I can verify by putting the positive tip to the left leg of the LED, the potential is almost down to zero. It's only at 0.01, roughly, even less volts. And as soon, obviously, as I connect it to the negative terminal, it's really down to zero. Now there's absolutely no potential which I am measuring. So potential, this is what you need to remember, is always relative to the negative terminal of, for example, the battery or the power source you are using for your circuit. Now let's talk about voltage. Voltage is always about a difference between 2 points. Voltage and potential can be identical if I choose voltage to be measured between, let's say, an arbitrary point on the circuit and the negative terminal. That's both a potential and a voltage, but I can also use voltage to express the loss of potential energy across a certain element, such as this resistor here. Let's put the negative terminal of the measurement tip to the lower part of this resistor here and the positive to the top. Apply a bit of firm pressure here, and you can see, now I've lost connection, and you can see here that the voltage drop across this resistor here is 3.26 volts roughly. So if I again relate it to the negative terminal, you can see it's 8.73 and the lower part is 5.47. You can see that the difference between these two potentials is the voltage drop across this resistor, which is 3.25 volts. The same holds for the second resistor, which I can measure by putting the measurement tips to the upper and lower leg of this resistor here, and it's almost identical, 3.251 volts. So a small difference to the first one, which is related to the tolerance of this device. Now for the LED, the voltage drop across the LED, as you can see, is 2.2 volts, and this is the potential energy, or this relates to the potential energy which is lost when the charges transfer flow through this light emitting diode here. For now, that's all. I hope you enjoyed the video. If you have any questions, please do not hesitate to drop me a question down below in the comments. I wish you a nice day. See you next time here on The Fearless Engineer.